So welcome back. In computer science, many data structures like lists or trees have a non-bound depth. But for the moment, we are unable to define such data structure because we only have seen flat data types. So let's try to do it informally. On the paper, we would write that a list of integers, for instance, is either an empty list or an integer followed by the rest of the list. This looks exactly like a subtypes. And what you just have to realize is the fact that the rest of the list is also a list. So you just have to reuse the name of the type that you are defining inside the definition of this type. So we will be able to define deep data structures using recursive types. So for instance, if we want to define an algebraic data type corresponding to integer list, we need two cases. The first one is the empty list, and the second one says that a list which is not empty first comes with an integer, which is followed by an integer list. So we are reusing the name of the type that we are defining. This is a recursive type. If we consider this definition of a list, then if we write something like some element 1, some element 3, followed by empty list, then in fact in the machine the representation of this value is exactly a linked list like the one that you can find in any textbook about data structure. So a sum type can refer to itself into its own definition. And such a sum type is therefore recursive. Functions over recursive types are often defined by case analysis and recursion. So let us consider the type for list of integer. And now imagine that we want to compute the length of a list. We have a base case, which corresponds to the empty list. In that case, an empty list has a length which is equal to 0. So we just return 0. Now imagine that we have a list that has an element, and this element is followed by a sublist. Then to compute the length of this list, we just have to compute the length of the sublist L and increment it. In the end, what we get is a function from int list to int. Actually, lists are so important in functional programming that there exists a predefined type for list. It is written T list, where T is the type of the element of the list. The empty list is written using two brackets like this. And in fact, it's just a special syntax to represent the tag for the empty list. If you want an integer I to be followed by the rest of the list R, then you just have to write I : R. And in that case, : is just a special syntax for the constructor SOMELEMENT that we had in the previous definition. Finally, there exists a syntax to define a list by enumeration of its elements. You just have to write between brackets the expressions corresponding to the element of the list, separated by semicolons. So, as there is a predefined type for list in OCaml, we don't have to declare a list of integer, And we can define the length of the list by using the notation for the empty list with the two brackets and the notation for a list where X starts the list and is followed by XS using the double colons. This one is accepted, and here we see that OCaml has inferred that the input of this function is the standard list type. Now we can compute the length of a list composed of the integer 1, 2, 3, and it is indeed equal to 3. Imagine now that we want to define a function that takes a list and reverse it. Again, we can reason inductively by just considering the base case, the empty list, and in that case, reversing the empty list is the empty list. And so in the second case, we have a list X followed by XS, and what we want to do is first to reverse the rest of the list and concatenate the head of the list at the end of the reversed list. To do so, we use this at operator, which is predefined in OCaml. What we get in the end is a function from list to list, and indeed, it is reversing the input list. So let's come back to this reversal of a list. We iterate over the list, and for each element, we concatenate two lists. And the cost of this concatenation is linear in the size of the first list. So what we get in the end is a quadratic algorithm. This is a bit costly, and we want to throw away costly function. Here is another way to implement reversal, which is based on a technique called accumulation passing style in functional programming. The idea is that we add an extra argument that will contain the final result of the computation. So here I call it AQ. When we have finished traversing the list, so when we have an empty list, we will return the final result, AQ. And when we have a non-empty list with X as a head, we will push that element at the top of the list AQ and do a recursive call to the rest of the list. In fact, this is a way to reverse a list which has the advantage of being linear in the size of the list because we traverse the input list, and at each step we only do a constant time operation, which is the fact that we construct a list with X counts AQ. We can check that if we start with the empty list for AQ, at the end we obtain a reverse sync function from list to list, and it is working. Of course, you don't have to always have only two cases when you define a function by recursion of a list. Sometimes, as in the example you already seen in the first week, we can have several cases. For instance, here the cases were for the empty list, the cases for a list that only contains one element, and the cases for lists with more than two elements.